Hello everyone. Today we have this question from the flight mechanics. Now let's read to the following question. Consider a jet-propelled airplane with the following parameter. The wing area is 51 meters square, the wingspan B 25 meter, the zero lift drag coefficient CDO 0.02, the Oswald efficiency factor E 0.85. The thrust specific consumption TFC equals 0.62 kilonewton per kilonewton hour. The operational empty plus pilot mass MOP 8,518 kg. The aircraft have to deliver a payload of 887 kg by airdrop from the air point at A to B. The distance between the location A and B equals 2,000 km. The mission consists 3 phases. 1. Climb from the airport to location A to 10,000 meter altitude, whereby the air density equals 0.41 kg per meter cube. 2. Cruise to location B. 3. Cruise at the same altitude back to location A. The payload is dropped by parachute at location B from the altitude of 10,000 meter. Ignore the descent phase at the end of the mission. The fuel consumed during the climb phase is MFC, which equals 500 kg, and the distance covered during the climb phase is 100 km. The gravity acceleration is G 10 meter per second squared. Calculate the minimum amount of fuel required for this mission in kilogram. Once again, calculate the minimum amount of fuel required for this mission in kilogram. First of all, we can approach this question by printing out all the parameters from the following question. So therefore, to start this, by printing out the parameters, we have the S, which is the size of the wing area, where S equals 51 meters square. The span B equals 26 meter. The CDO equals 0.02. We have the Oswald efficiency factor 0.85. We have the TSFC, which is 0.62 kilonewton per kilonewton hour. We have the operational mass, which is the MOP, which equals the mass of the empty aircraft plus the pilot. MOP is given 8,518 kg. We have the payload, which is 887 kg, and this was dropped down with a parachute at airport B. So we can give it a coded name with M payload, which equals to 887 kg. And we have the range distance from airport A to B, RAB, which is 2,000 km. which is 2 to 10.6 meter. We have the altitude of the aircraft for the straight level flight at the density of 0.41, which is 10,000 meter, and this will become 10 to 5 meter. We have the density 0.41 kilogram per meter cube. We have the mass of fuel consumed by climbing, MFC, which is 500 kilogram. We have the range covered during the climb, or the distance covered during the climb, which is 10. 600 kilometer. That will give us 10 to 5 meter. We also have the acceleration due to gravity, which is 10 meter per second squared. Now, from the question, we have to find the minimum amount of fuel required for the whole mission. So we can give it a coded name as minimum fuel to be calculated. Now that all the parameters is being pulled out, first of all, we need to calculate the aspect ratio. The aspect ratio of the aircraft is b squared over s, and that gives us 26 squared over 51. This gives us 13.26. So our aspect ratio is 13.26. From here, we can find our CL and CD. That is the CL and the CD. What CL, which equals pi over 3 EAR CDO. And CD equals 4 over 3 CDO. By using this formula, we can slot in all our value. Our CL becomes pi over 3 multiplied by E, which is 0.85 times the aspect ratio, which is 13.26 times the CDO, which is 0.02. Our CL calculated will be 0.4859. Our CD equals 4/3 CDO, which is CDO is 0.02. Our CD equals 0.0267. Now that we have found our CL and CD, we can use what we call the range equation from the Bregret formula. And what do we mean by the range equation? One over TSFC square root of HG over rho x multiplied by CL over CD at maximum MO minus M1. So this is what we call the Bregret equation theory. So therefore, by using this formula, we can assume that this becomes a K factor. And how do we calculate our K factor? 1 over TSFC multiplied by HG over rho S CL CD, then our TSFC in hour becomes 3,600 over 0.62, the square root of 8 times 10 over 0.41 times span, wing area S 51, then our CL calculated, which is 0.4859 over 0.0263. Our K factor from the Bregret equation, which is a constant value, equals 2.97 10 to 5. Now that we have our K constant from the Bregret equation, now we can start comparing the size of the fuel and the sequence of the flight stages. Now, how do we do that? First of all, we know that the aircraft dropped the payload at airport B and it returned back to airport A. Now, we can deduce this by using this formula. That is to say, the range from B to A, that is, when the aircraft is returning from B to A, equals the K constant to the mass at B minus mass of the operational. From here we can deduce that the mass at B equals the range of B to A over K constant plus MOP all in square. So therefore our MB equals 2 to 10 to 6 over 2.97 to 10 to 5 plus 8518, which is the mass of operational, all squared. Our calculated MP, that is the mass at B, equals 9806.35 kilogram. That's the mass at B. Also, why the aircraft returned from A to B, that is RA to B this time around, equals, that is the range from A to B, becomes the range of the climb, that is the distance covered during the climb, plus the K factor of the Broguet equation, because MA minus the mass at B plus the payload. There we can single out MA, which is MA equals range from A to B over the K factor minus range at the climb plus mass of B plus mass of payload, all squared. Our MA equals 2 to 10 to 6 minus 10 to 5 over 2.97 to 10 to 5 plus square root of 9806.35 plus 887 all squared. Our calculated MA equals 12,056.35 kilogram. So therefore, now that we find MA and MB, so the minimum fuel for the whole mission MF equals MA minus MOP minus MPL minus payload plus the mass during the climb. MF equals 12,057.35 minus 8518 minus 887 plus 500, it gives us 3152.40 kilogram. So the mass of minimum fuel equals 3152.40 kilogram. Thank you for staying tuned.